Hello, physics babies. Whether we're in person, like you, or remote, like you, we're still moving on into brand new fancy physics. So we're going into our fourth unit. We're going a little bit fast. We're going to slow down this week and next week, but we're going to talk about some more important stuff using Newton's laws in new and advanced ways, and we're going to learn that some stuff we learned last unit was not quite always true, but we're learning better rules that are more true more often, and they're going to be super great. So let's all do this problem. Great job, it's choice 2, 1600 newtons. Normally, this man would accelerate downward at 800 newtons due to gravity. No, normally this man would accelerate down at 9.8 meters per second squared due to the 800 newton force of gravity downward. But since we know his acceleration is actually upward of 9.8 meters per second squared, he must have a net force of 800 newtons upward. If the net force is 800 upward and gravity is 800 downward, there must be an additional 1600 newtons upward from the elevator on the man, which is the normal force, and it's choice 2. Okay, so we're going to discuss some fancy stuff. There's a lot of theories in the world about how the moon was created, and one theory looks like this. There was a very large asteroid or comet or something, and it hit the moon and knocked off a whole bunch of dust and stuff. But we don't have a bunch of dust and stuff. We have a big solid moon. How'd that happen? Check this out. Okay, so obviously if something large were to hit the Earth and blow all this dust and debris into space, most of it would eventually come falling back down into Earth. But this simulation shows that some of that dust and space rock junk would eventually, instead of coming back into Earth, just kind of form up with other pieces of dirt and form solid objects rotating around the Earth. And in fact, eventually all come together and form a giant moon. So that's a very common theory about the formation of the moon, maybe like 4 billion years ago. Wow, great. Okay. So today we're talking about gravity, and we're going to start with a real simple formula. What's the weight of, I don't know, a 1 kilogram baby? Oh, I know, Mr. Lamb. Yes, Hazel? It's 1 kilogram. No, that's a mass, not a weight. Yes, Daisy? Oh, it's 9.8 newtons. That's right. There you go. This is the mass. If we want the weight, which is also known as the force of gravity, we use this formula, m times g. 1 kilogram 9.8 meters per second squared. 9.8 kilogram meters squared are also known as newtons. Good job, Daisy. Okay. This is the rule we learned. Today we'll learn this rule is not always true. It's true in some specific cases, and we'll learn a more general rule that's true more often. A lot of science is like that. You learn one rule, then you learn when it's not true, and the rule for other times as well. I just keep doing that over and over again. So this is true, but it can't always be true. Think back to Earth science, not about the formation of the moon. Think about tides. What causes tides? You've probably seen pictures like this. Okay, I didn't draw it that well, but it's fine. The moon causes tides by pulling the water on the earth. Does the moon have so much gravity that it can pull water all the way from the earth? Does the water on earth ever just kind of fly away and go up into space? No. So as we saw in the simulation and we see in tides, the earth has gravity, the moon also has gravity. Why does the earth's gravity affect the water more strongly than the moon does? How come water is attracted to the earth more than the moon? There's two reasons. Tell me one of them right now. Okay, Sage. How come the earth pulls this water harder than the moon? Because it's heavier, it has more mass. That's right. The earth has more mass than the moon. So, water, in general, is pulled to the earth more than the moon. That's why there's lots of water on the earth and less on the moon. Not really, but pretend it's right. Okay, so yeah, gravitational force is dependent on the mass of the planet or star or whatever pulling the thing. But what else is it dependent on? That can't be the only reason. Sure, water doesn't fly up off the earth toward the moon because the earth is heavier. But the sun, can you see that? Yeah. The sun is way heavier and more massive than the earth. It's not drawn to scale. Does water ever fly up off the earth and go to the sun? No, otherwise we'd be kind of out of water and very, very thirsty, which is very, very bad. So what's the other factor? We said mass is one factor, but the sun has even more mass. So how come gravity from the sun isn't stronger than the earth on the water in the picture? Tell me now. Yes, Hazel? Distance. Good job, yeah. The water is pulled to the earth more than the moon because the earth has more mass. So mass is one factor. The water is pulled to the earth more than the sun because of the distance. The earth is much closer. So everything has gravity, even like a little speck of dust in space. It's depending on two factors, the mass of that object and the distance to the object from another object. Let me be more specific. Any two objects in space have gravity between them. The Earth and the Moon, or even like a satellite and an asteroid, or the Sun and like a supermassive black hole, or something like that. Any two objects have gravity between them. That force depends on two things. One, the mass, and two, the distance. Mass and distance. So, let's make a new formula. Here's our old formula. Here's our new formula. And let's see if this works for my example before, a 1 kilogram baby on the floor of my house. That's what babies look like. Perfect. A great drawing by a great artist for a great lesson. So on the old formula, we figured out that for a 1 kilogram baby, the force of gravity is about 9.8 newtons. This little baby, must have been born very recently, is only 9.8 little apples. let's see if we can find a new formula where that's still true. So what affects gravity? All we knew already was the mass of the object. The bigger the mass, the heavier it is. That's still true. In this new formula, M1 is my 1 kilogram baby. The heavier the baby, the more it weighs. So that still works out. What's M2? Well, what's the force on the baby from? I always am really specific with, oh, there's a force from this on this. Well, what is gravity from if it's on the baby? It's from the Earth. Okay, that's good. We need to know the mass of the Earth. I have it memorized. It's 5.97 times 10 to the 24th kilograms. Everyone knows that. Cool. Now we need R. Remember how we said that the sun's gravity is not as strong as the Earth and the moon's because it's so far away? Yeah, R is the distance between the objects. And you might say, my baby's on the ground, so R is 0. That's not going to work. No good. Look at my baby. Look at the Earth. Yeah, sure, they're very close to each other, but they're not really 0 meters from each other. Maybe this little piece of baby is very close to this little piece of Earth, but this piece of baby, like the baby's head, is very far away from this piece of Earth, which is like, I don't know, like I guess China. They're very far apart, so we can't use the distance between them. We have to use something very, very smart. Use the distance between their centers of mass. So we don't measure from the top of the baby or the bottom of the baby. Measure from the center of the baby. That's not really important, because we don't measure from this part of the Earth or this part of the Earth. Measure from the center of the Earth. So basically, we're using the radius of the Earth plus like 10 centimeters for the baby. We can ignore that 10 centimeters, because when we do sig figs, it doesn't matter at all. So the radius of the Earth, obviously I memorized that too. Everyone knows it's 6.4 million meters. Okay, so that's R. It's not a radius all the time, but it usually is the radius. It's not a radius, it's the distance between the centers of the objects. But if one's really big and one's really small, it's basically the radius of the bigger object. Not always true. If it's the Earth and the Moon, I don't know why I drew another Earth. I had a great Earth right there, but this one's also good too, so I did a great job both times. It's the distance from the center of the Earth to the center of the Moon. That's R right there. It's not the radius of the Earth. It's the radius of not the radius of the Moon. It's the radius of the Moon's what? Yes. Orbit. The radius of the Moon's orbit. Wow, good job. Okay, we're missing one big thing. 6.67 times 10 to the negative 11th power. Wow, very small number. Newton meters squared per kilogram squared. This is a very fancy value. It's called the universal gravitation constant. It was found by a fancy scientist named Cavendish, who we don't really need to care about, so I didn't really bother memorizing his name. But he had this fancy experiments where masses rotated a thread, and he measured the angle with a mirror and a light, and he figured out big G. Don't memorize Cavendish, memorize this. Never just say gravity. You'll confuse little g, big G, and FG. Fg is the force of gravity, also known as weight. Little g is acceleration due to gravity or gravitational field strength. Big G is universal gravitational constant. It's in Newton meters squared per kilogram squared. Those are crazy units. Don't worry about what they mean. The meters cancel meters squared, and the kilograms cancel kilograms and kilograms. So it comes out newtons, which is what we want. If you want to be fancy, you can say, oh, a Newton is a kilogram meter per second squared. So you could say that it's actually 6.67 times 10 to the negative 11th meters cubed per second squared kilogram, which also makes no sense. If you try to think about what the units mean, they don't really make any sense. But just trust they're the correct units so that when you do the calculation, the force comes out to be measured in newtons. Okay, great. So let's do the calculation with our trusty calculators. Beep, beep. Just kidding. Take out your calculator and type in all those values for a 1 kilogram baby. 6.67 times 10 to the negative 11 times 1 kilogram times 5.97 times 10 to the 24th kilograms divided by the radius of the Earth squared. 9.7 newtons. It's too bright. Help. 9.7 newtons. And what did we find earlier? 9.8 newtons. Wow, it's like 1% error. Good enough. Leave it there. We did a great job. We are physics scholars. We know physics. Hooray. We got the same value, but this is more useful because you can use this not just for babies on Earth, but for the moon and the Earth, for the Earth and the Sun, for the Voyager spacecraft and Alpha Centauri, for any objects anywhere in space, as long as you know the mass of one, mass of the other, and the distance between their centers of mass. Okay, what else did I feel like saying? I know. How did I know the R is squared? Yeah, we know a bigger mass has more gravity, so two things we know from this formula. A bigger mass feels more gravity, which makes sense. A fat baby is heavier than a skinny baby. A larger mass has more weight. I held up two babies that had the same mass, but pretend I didn't. A larger mass has larger weight. We know that. A larger mass also exerts more gravity. And the Earth pulls the baby with a lot of force. The moon has less mass, so it would pull the baby with less force. Jupiter has more mass. The baby is on Jupiter, the baby will experience more force. So we know that M and M make sense. We know R also makes sense. The farther you are from the Earth, the less gravity. That's why, pretend that's why. That's why astronauts in space are weightless. But why is it squared? I'll tell you. No, you'll tell me. That's what I meant to say. Imagine I have a light bulb. A light bulb produces a certain amount of light waves, and they go out from the light bulb in all directions. I know. Yeah, that's right. If I put a light bulb inside a 1 meter radius sphere, then all the light waves would be spread out on the walls of the sphere. right? Right, yeah. A light bulb's in a hollow 1 meter sphere. All the light waves that come out of the light bulb are spread out over the surface area of the sphere. What's the surface area of a sphere? Four pi r squared. 4 pi meters squared. Good job, me. Thanks. What if I had a bigger sphere? I got a 1 meter radius sphere and a 2 meter radius sphere. And I put a little light bulb inside both of them. Well, in both cases, all the light waves that come from the light bulb will hit the outside of the sphere, right? Right. In this case, they're spread over a surface area of 4 pi r squared, which is 4 pi meters squared. In this case, they're spread out over the surface area, still 4 pi r squared, 16 pi meters squared. So, if the light is spread out over the area of a sphere twice as big, it's spread out over an area 4 times as big. I double the radius of the sphere, I quadruple the surface area of the sphere, so the sphere is lit up 1/4 as much. And this is true for all light bulbs and all spheres. The amount of light hitting the outside of the sphere is proportional to 1 over r squared. You guys have seen like the little alpha for proportional to? Well, now you have. Light is proportional to 1 over r squared, where r is the distance from the light to the observer. Well, that's true for light waves. It's also true for gravity waves. Gravity from the Earth is shot out in gravity waves all around space. Some of them hit the moon, some of them hit the sun, some of them go off and are totally lost. Some of them hit babies who are sitting on the ground listening to a great lesson. But the amount of gravity waves you get hit by is proportional to 1 over r squared, how far you are from the Earth's center squared. Are gravity waves a real thing? Maybe. Are they part of AP Physics 1? No. Just know this formula. I like M1 and M2, but sometimes you see big M and little m. So let's try that. Let's say we have a big planet of mass big M and a little UFO kind of alien frog of mass little m. The force on the spaceship from the planet would be G m over r squared. That's the force on the spaceship from the planet. Tell me the force on the planet from the spaceship. Well, if you find the force on the planet from the spaceship, you switch M1 and M2, but R is the same. So the force on the spaceship from the planet is this. The same force exerted on the planet from the spaceship. And how could we have known that without solving? Yes, good job everyone. Newton's third law. I drew it kind of weird. This is the force on the spaceship pulling it toward the planet. This is the force on the planet pulling it toward the spaceship. I think we already discussed why the spaceship experiences more effect than the planet. If you don't remember, ask me in class. And don't be confused. The last thing, gravity always attracts masses to other masses. Any mass in space is attracted to every single other mass in space. And every student in the class is attracted to every other student in the class, because that's the way gravity works. It always attracts masses to each other, depending on how much mass they have. So, that's cool. If you're ever asked about the direction of the force of gravity, it's always, toward each other, from one toward the other, in the direction of the planet or the star or the spaceship. That's gravity, so bye.